Okay, so we're going to be introducing the concept of elastic energy today. Um, if you remember, when we looked at springs, we looked at elastic strings, and we looked at this idea that when you stretch them, or in the case of springs, when you compress them, you've got this tension. And the tension, it varies. It varies linearly with the extension from the natural length of the string or the spring. What we haven't talked about yet, though, is the energy changes that are going on, or at least not in enough detail. So there have been some string and spring problems that we haven't been able to tackle yet, and it's because we haven't introduced this concept of elastic energy. So we're going to define it today. We're going to derive the formula for it, and we're going to start using it. So to just get us started, I just want you to visualize this particular scenario. It's the usual thing where you've got an object hanging from the ceiling and there's a spring attached to the ceiling and a spring attached to the object. So imagine you've got a heavy mass, it's attached to a spring hanging from the ceiling, and I hold this object so that the spring is at its natural length. So it's at rest, and then I let go, and then what happens? So visualize that situation, and hopefully you can see that what's going to happen in your mind's eye is that the object drops, and depending on the modulus of elasticity, the object's probably going to oscillate for a bit. It might bounce up and down for a while, and after some amount of time, because of dampening and because of properties of the spring, eventually the object will settle into a resting state. The thing is, though, that resting state is obviously going to be lower down than when I first dropped the object, right? I'm not gonna let go. It's not gonna then bounce up and down and end up where it started. It's gonna end up lower down. Now that hopefully makes sense, right? It's at the point where the tension in the spring upwards is balanced by the gravity downwards. The question, though, is when we consider the energy, it seems like something's been lost, right? The kinetic energy started at 0 and it ended at 0. The potential energy, it was some amount, it was above the Earth by some height, but now it's lower. So potential energy has been lost. So explain this. What's happened to the conservation of energy? If the potential energy, the gravitational potential energy has been lost, what has happened? So have a think about that for a moment. And then we'll see if you've got the right idea. So in this case, you may have thought some ideas about the spring dampening or energy being lost to the environment, because as the spring bounces up and down, there's some sort of energy being lost in some sense and not contained within the system. But actually, most of that energy hasn't been lost out of the system, and in fact, going forward, we're going to be modeling it as a perfect spring anyway, and by perfect I mean it doesn't lose energy to the environment. What's happened is that potential energy is now stored within the spring itself. So it's a different form of potential energy, and we're going to call it elastic potential energy, or EPE. So it's just like gravitational potential energy, where when you lift an object up, some energy is lost in the work done in some sense, or some energy is transferred, but that transfer of energy has now resulted in an increase in potential gravitational energy. Whereas in this case, with a spring that's now lower down, you've got an increase in the stretch and therefore an increase in the potential energy within the spring itself. Okay, so that's the concept. Now let's look at the mathematics of it. So I want to derive the equation of elastic energy, the elastic potential energy. I'm going to just add the word potential here. And what I mean by that is, for a given extension, how much energy is potential energy elastically is stored in a spring, right? Let's stick with springs for the moment. With strings, it'll be very similar. So when a spring is at its natural length, maybe let's just draw a spring for a moment. Okay, so I've got a spring, it's at its natural length, so it's neither compressed nor stretched, how much energy is stored in the spring, at that point it's 0. And then let's say I stretch the spring a bit. I've stretched it by x. How much energy is now in here? I say in there, it's more of a concept really. It's not literally in the spring, but in English we'll say it is in. So we say the energy is stored within the spring. How much? Right? Is it a multiple of x or some other function? And in order to derive that, we're going to think a bit about the tension formula. So if you remember, we had the tension in a spring is lambda times that extension divided by natural length. And now let's draw a graph of how the tension varies with extension. So if I have extension along here and tension along here and 0, 0, well, at 0 extension I've got 0 tension. And then if we look at this formula, I mean, this is effectively just a straight line, isn't it? Because it's lambda over L as the gradient, and these are constants, times x. So it's a straight line with gradient lambda over L, where lambda over L are some constant, depending on the properties of the spring. So we'll have something that looks like this. Okay, straight line. And now let's think about, what does the area under the graph represent? Okay, sometimes areas under graphs are meaningful, sometimes they're not. In this case, what this area effectively is tension times displacement, or in other words, it's force times, displacement, I suppose, or distance. And what do we know about that? If you multiply a force by a displacement, you're effectively going to get energy, right? You're going to get work done. So this is work done, or energy. Okay. So this is where the elastic energy comes from. You stretch a spring, and as you stretch it, you've got a force in that spring, or applied to the spring, that you're working against, and that force is changing. It's changing instantaneously, and that's why the area is not a nice simple multiple of x. It's actually a function of x, but it's still not a very complicated one. So we just got to find the area under this curve, basically. Let's pick a specific value for x. So x is the general variable. Let's say x0 is our actual distance. Okay, so I'm going to stretch the spring by x0. What then is this purple area? So it's just an area of a triangle, right? It's going to be x0 times the height. So if that's x0 there, then the y value is going to be lambda x0 over L. Multiply those and divide by 2. So we'll get lambda x0 squared all over L all over 2. And that's it. That's the formula for elastic potential energy. Except you won't see it as x0, you'll just see it as x, because when it's just the formula, there's no ambiguity between the variable and the instance of the variable. So here, x just represents the actual value of the extension. Okay, so that's our elastic potential energy formula. It's quite simple to use. It's very similar to this tension formula in how you'll be using it, except this one gives you tension and this one gives you elastic potential energy. There is one other way you can think about this area. I'll quickly jot that down if I make some space here. Rather than graphing it, you could also think of it this way. The elastic potential energy is effectively the integral from 0 to x0 of the function of tension times distance. So in this case, that's lambda x over L. And then multiplying by these infinitesimal displacements, we've got dx. Okay, hopefully that makes sense to you if you think of the integral as being a sum of an infinite amount of tiny products. So you're multiplying tension here by displacement here, that's the dx, the infinitesimally small displacement or change in displacement. And that should give you the same thing. From 0 to x naught, you integrate that, you will again get lambda x naught squared over L. Okay, so that's the concept. This is the formula though. Worth remembering, it may be in the formula book, but again, this is one of the commonly used formulas that's common enough that if you haven't remembered it, it just means you haven't done enough revision. So make sure you start taking note of this one in addition to this one here. So let's take a look at how we use it. Okay, so an elastic string, so it's a string this time, just in case that's relevant. It probably won't be for the easier examples. Natural length is 1.4. Modulus of elasticity is 6. Find the energy stored in the string when its length is 1.6. So if its length is 1.6, its extension is 0.2. And then we're going to write EPE, elastic potential energy, is equal to lambda times x squared all over L times 2 equals, and then you work it out. In this case, it comes to 0.0857 joules. Okay. Okay, and in this case, we've got a light elastic spring. Again, I don't think it makes much difference if it's a string or a spring. It has a natural length of 0.6, modulus of elasticity 10. Find the work done in compressing the spring from a length of 0.5 to a length of 0.3. So remember, the work done to compress it, because that work is not going to be used for anything else, you're not lifting a mass attached to it, for instance, that work done is going to be entirely transferred to elastic potential energy. So this is equivalent to just finding the EPE. They're not always going to be equal, but in this specific case they will be, because there's nothing else for that work to transfer to. It's only being transferred to elastic potential energy. We do have to be a bit careful here though. There's actually an easy error to make, which I'll point out, but let's just show the right way to do this. So at these two extensions, we're going to consider them separately. At a length of 0.5, so at length of 0.5, our x is effectively 0.1. We're not going to worry about putting minus 0.1 or anything like that, because we're just going for the a positive value, and in any case it will be squared. And then to a length of 0.3, we've got an x of 0.3. So then we need to find lambda x squared over 2l, and again here lambda x squared over 2l. But remember, the x's are going to be different for each of these two cases. So in the first case here, if you do 10 times 0.1 squared divided by 2 times 0.6, we get a 12th. I won't show the full working, but that's what we get. And in the second case, we've got 10 times 0.3 squared divided by double 0.6, and there we'll get 3/4. So what that tells us is that when it was at length 0.5, it already had this much energy stored. So there was already some elastic potential energy in there of a 12th. And after compressing it further to a length of 0.3, there was now this much elastic potential energy. So the work done only contributed to the difference between those two. So to get the work done, we're going to have to find the difference. And in this case, we get 8 twelfths, 2/3. And that's it. That's the work done. Yeah, 2/3 of a joule in the work. So then before we look at questions for you to do, I just want to point out a common error which applies very much to the example we just looked at. And that is when you're doing the change between two different states of compression or extension, you can't just find the difference between the displacements and then use that in your formula. So on the previous slide, notice that we calculated the EPE 2 different times completely independently and then found the difference. So what you can't do, for instance, is say if I have an extension 1 and an extension 2, to then do lambda extension 2 minus extension 1 squared all over 2L. You can't do that. That is not going to be the EPE. In fact, I don't think that's anything particularly meaningful. What you should be doing is what we did on the previous slide, which is as follows. Okay, it might seem obvious, but it is easy to make that mistake, especially early on if you're not familiar with this formula so much. So keep that in mind. Also, whichever way around this is x2 or x1, it depends on which one's the smaller number, which one's the bigger. Ultimately, if it's energy, you should end up with a positive number. Okay, cool. All right, so let's look at some questions. So I've got 3 on this slide and 1 on the next slide. That first one is just a little bit of calculation, making sure you don't make that mistake that I just talked about. 5 is a little bit tricky. Then have a go at 6, and once you've had a go at those 3, check your answers. There's one final question on the next slide. So you can pause the video now and try these 3. Okay, and then take a look at this question here. Part A is mainly a bit of revision on calculating the tension, and then once you've done that, have a go at part B. Okay, you can pause the video now.